Hello, everyone. Welcome to Stat 479, Lecture 16. So here we're going to continue our discussion into directed acyclic graphs and go into them in more detail. And in particular, just talk about this correspondence between the multivariate distribution and the graph structure. And then we're going to go into a very specific kind of model that naturally lends itself to directed acyclic graphical models, which are linear structural equation models, and they're kind of widely used in a lot of areas, particularly in the social sciences. So just to remind everyone, so the DAG model consists of a directed graph G, and then we'll talk about how it relates to the distribution shortly. So for the DAG model, there's this graph G which consists of vertices and edges. So the set V, because we're trying to link this back to this multivariate distribution, the set of vertices is the p random variables x1 through to xp. And these random variables have dependence, and in some sense, the graph structure encodes some information about this dependence structure. And E is a set of directed edges. Xj, Xk is an edge or a directed edge, so it's very important that Xj is the parent of Xk. So I'll just write that down. So Xj is the parent of Xk. Okay, so we encountered two examples involving four nodes in the previous three nodes in the previous lecture. This first one we have the three random variables x1, x2, x3. So these are the vertices, and then the edges is x1 to x3, and then the other edges are x2 to x3, and then we also encountered this, and this was kind of referred to as that paradox where x1 is kind of independent of x2, but if you condition on x3, then x1 and x2 are dependent. And then we had this other graph example, directed acyclic graph example, where the edges, essentially the graph looks very similar, but the edges pointed in different directions. So the first edge was x3, x1, and the second edge was x3, x2. And this is kind of a very typical scenario of x3 being a confounder for x1 and x2. And the other thing that we talked about is that to ensure that this is acyclic, there has to be no directed cycles. And what that basically just means is paths from a node back to itself. And that means you can only walk in the direction of the arrow. So if there's no paths from a node back to itself along the directed edges, then then that's a directed acyclic graph. And this is an important property because it allows you to write out the distribution in a convenient way. And the other thing that we learned at the end of the previous lecture was the factorization over the DAG. So this is really getting at this relationship between the graph structure and the multivariate distribution. So you can say that so the distribution factorizes over a DAG G if you can write out this joint distribution as where you only condition on, so this joint distribution of the conditionals where you only condition on the parents. So okay, and so this is kind of why that notion of parents was so important. And this might seem a little bit obscure, but so if we look back at our example, so for example 1, we can, we worked out that we can write out this distribution as the marginal of f1 because x1 has no parents, the marginal of x2 because f2 has no parents, and the conditional of x1 and x2. Okay, and so and then for that second graph, we can write this out as, so f1 has just one parent, which is x3. F2 has one parent, which is x3, and then x3 has no parents. So this is how the distribution factorizes. Okay, and we're gonna see a very concrete example of that later as well. And so so one thing to kind of always bear in mind when we're talking about graphical models is that there's really two parts to think about: the distribution, and then the graph. So the distribution for any multivariate distribution has this form, and then for any graph, it obviously just is a set of vertices, which is the random variable, and then a set of edges. And then you kind of need a way to connect them. So, one way to so one connection we've already learned is factorization. Okay, and then we're going, and so this is since parents are a concept from graphs, and we're going to learn another a different characterization today, which is this notion of conditional, which I've touched on earlier, conditional dependence or independence. So we're going to see that the presence of an edge or not an edge is actually going to relate to a conditional independence. And just to remind people, so if we go back to our earlier example, or our earlier examples, remember that we had x1 independent of x2. We haven't sort of learned why exactly that's true. We'll get a bit of an understanding of that today. But then we also had that x1 is actually dependent on x2 given x3. But on the other hand, we have here that x1 is dependent on x2. X1 is dependent on x2, but x1 is independent of x2 if we condition on x3. Okay, and so and we can kind of we can relate this to factorization as well. Because remember that, so for 1 we have that so you can see that it follows that if we were interested in just the joint of x1 and x2, then that's just the integral of f1, x1, x2, x3. So all I'm doing is showing you how to do how to calculate kind of joints, which is just you integrate over the other variable, and so this you can clearly see is equal to okay, and you can see that we can take out anything here that does not depend on okay, and this whole thing is equal to 1 because we're just integrating a conditional distribution over the distribution that you're looking at. And so then this is just equal to f1 of x1, f2 of x2. So which implies that x1 is independent of x2 by the definition of independence that we're kind of used to seeing. And similarly for example 2, we have that so in example 2, just to write out the graph again and to do the factorization again. Okay, so if we look at the conditional distribution of f of x1, f of x2 given x3, then that just equals to over f3 of x3. So this is just the definition of the conditional distribution. Okay, and clearly we get the cancellations here that we're looking for, and so this clearly shows that so therefore we have once again that x1's independent of x2 given x3. So this is the So this kind of shows that for these two examples, okay, so the question is, can we generalize this? So I've kind of told you a priori that the edge and the non-edge corresponds to for graph 1 it corresponds to x1 independent of x2. For graph 2 it corresponds to x1 independent of x2 given x3. Can we actually generalize this? And we actually can, and this is a pretty useful and cool result that so for a DAG graphical model, G equals VE with PDF f of x1, x2 up to xp that factorizes so if we have this factorization, there exists an edge xj of xk if and only if we have this conditional independence relationship. Xj is not independent of xk given if we condition on all the parents of xj, and the parents of the union of the parents of xj with the parents of xk. Okay, so this looks a little bit complicated, but what we're saying here is that you can read conditional independences, or let me say it maybe this way. Each edge in a DAG encodes a conditional independence, or sorry, I should say conditional dependence. And each non-edge encodes a conditional independence. Okay. So let's kind of just this example is like this definition's a little bit to take in. So let's just spend some time on some examples. So example 1, okay, so in that case, we have that the parents of x1 equals the empty set, the parents of x2 also equals the empty set, and the parents of x3 is equal to the set x1, x2. Okay? And so, so we have that there's no edge between x1 and x2, and the other two have there's edges and then we have edges x1, x3, and x2, x3, And so what this tells us is that x1 is going to be independent of x2 given the set of parents. So that's the empty set. So we have this conditional independence, but then we also have that x1 is dependent on x3 given the parents of x1 and x3, which is just x2. And then we also have that x2 is dependent on x3 given the parents that we have, which are x1. So that's essentially what this statement's telling us. Okay, and from this you can actually conclude, and this is something that's beyond the scope of what we're going to cover in this course, but you can actually conclude from this that x1 is actually dependent on x2 given x3. There's a way, like, you can kind of show that that's true. But essentially, so for every edge, for every pair of vertices, there's potentially an edge or not an edge. And if we follow this definition here, then this kind of tells us what are the fundamental conditional independences or dependences in this graph. So then the second for the second example, we have x1, x2, and x3. And then we have that the parents of x1 is equal to the set x3. The parents of x3 is equal to the set x2. And the parents of parents of x2 is equal to x3. And then the parents of x3 is again just the empty set. There's nothing in that. So so we have that this first relationship, x1 is independent of x2 because it's so let me just be a little bit more precise about this. So we have that no edge between x1 and x2 implies that, or that's an if and only if statement, that x1's independent of x2 given the parents of x1, parents of x3, and the only parents here are x3 here. So therefore we have that x1's independent of x2 given x3. But then we also have that so an edge between x3 and x1. So that implies that x1 is dependent on x3, and that x1 is dependent on x3. Sorry, and because the parents of x3 equals to is equal to the empty set, and the parents of x1 is equal to x3, and we don't include x3 here because you don't condition on something that's in the set. So to be precise, I should actually say the parents of x1, x3, excluding xj and xk. So we're not including those two variables when we're conditioning. So, and then also we have the edge between x3 and x2 means that we have x2 is dependent on x3. So the three kind of fundamental independences we have or dependences is that x1's independent of x2 given x3, x1's is dependent on x3, and x2 is dependent on x3. And you actually put these together to show that x1's dependent on x2, because if those two statements are true, that implies this this statement, just like we saw in the in that first example here. Okay, so again, this is a bit sort of new to get, these kinds of concepts are pretty new to get your head around. So we're going to kind of stick with some pretty simple examples, and then we'll move on to kind of a concrete set of parametric models. Let's do one more example that we haven't seen before and that has more than 3 nodes. Or I think we saw this once, but we'll do it. and we'll see both the factorization. Okay, so we have x1, x2, x3, and x4. Okay, so this is our V. Okay, and you can see that this is a DAG because there's no directed cycles. If the edge from x1 to x4 was reversed, then this would not be a DAG because you could move from x1 back to itself in cycles. So this is not, so we've chosen this, so this is not a DAG. And so the edge set here is clearly, there are 4 edges. Okay. So we also note that the parents of x1 here is equal to the empty set. The parents of x2 is equal to the set x1. The parents of x3 is equal to the set is just x2. And x4 actually has 2 parents, which are x1 and x3. Okay. So the factorization that we, so let's kind of first do this through the factorization. So we're going to say that, wrap this up at the end, but there's 2 ways to think about the connection between the distribution and the graph. One is through factorization, one is through the conditional independences. And so they're essentially equivalent, but we'll go through both of them here. So we have that f of x1, x2, x3, x4 equals so this is the definition of the factorization. And so that's x1 has no parents, so it's just x1, and then x2 just has 1 parent, which is x1. X3 has 1 parent, which is x2, and then f4 has 2 parents, which are x1 and x3. Okay, so this is the factorization. And one thing I just wanted to kind of quickly say here is that so if we use chain rule, if we use the chain rule, and I just kind of want to talk about like what, like another way to kind of interpret this, because this is potentially quite new for a lot of you. So if we use the chain rule, f of x1, x2, x3, x4 is equal to, f1 of x1, f2 of x2 given x1, f3 of x3 given x1, x2, f4 of x4 given x1. Sorry, I'm going to split it up. I'm going to multiply it by f3 of x3 given x1, x2, and then f4 of x4. So this would be true for any distribution. So true for any distribution with 4 variables. So one thing to note here is what's the difference between this expression here and then what we see for the DAG. So you'll notice that this x1 is missing, and then here we have this x2 missing here. So, and this comes back exactly to the DAG structure. So the reason why the x1 is missing is because so x1 missing in f3 of x3 given x2 because no edge between x1 and between x1 and x3, and then x2 missing in f4 of x4, we only condition on x1 and x3 because there's no edge between x2 and x4. So this is just kind of giving you some insight about if we didn't like have any graph associated with the distribution, we would just have this expansion due to the standard chain rule. But by using this this graph expansion, we're actually kind of reducing the number of variables in the distribution because we're conditioning on less, because there's in some sense the lack of an edge, as we've talked about, is related to conditional independence. Okay, so now let's go back to what that was a bit of a side note or a different way to interpret the factorization. Now let's do things in terms of conditional independence. Independence/dependence. So remember that we have that, so there's like an edge xj, xk, if and only if xj is dependent on xk given like when you condition on the parents, but we don't include the variables xj and xk in there because you don't want to kind of condition on yourself. Okay, so just as a reminder, so there's 6 sort of pairs that we have to look at. So we first look at the edge between x1 and x2. Then we look at the pair x1, x3. So there's always p choose 2 pairs, x2, x3. So we're going to look at them. Let's just look at them this way. So x1, x4, and we're going to look at them one at a time. x2, x3, and then x2, x4. So all I've done is just selected the I've selected the 6 kind of pairs of variables that we have, and we're going to see if there's a conditional independence. So we have an edge between this, so that means that it's a dependence thing. And then what is the dependence? It's the we've got a condition on the parents, but there's no parents to condition on because the parents of x1 is just empty, and the so this has like, I'll just put in brackets, no parents, because the only parent of x2 is x1, and we exclude that from here. x1 to x3 is no edge. So that means we have a dependence, and we have to condition on the parents of x2 of x3, which are x2. So x2 is a parent of x3, so we need to condition on that. x1 to x4, there's an edge. So what that tells us is that x1 is dependent on x4, and we need to condition on all the parents, and the only parent of x4 that's not x1 is x3. And then similarly, if we have from x2 to x3, there's an edge. So that means we have x2 is dependent on x3. And then I've missed one here. So it should be x3, x4. But we'll do that later. So the only parents of x2 and x3 are x1. So we condition on x1 here. Then we also have that, there's no edge between x2 and x4. So that means that we again have an independence statement that's x2 is independent on x4 given the parents. And there's two parents here, x1 and x3. And then there's an edge, and which means that we again have this dependence relationship between x3 and x4. And we condition on the parents again, which are x1 and x2. Okay, and just to kind of, for our own sort of sanity, we're going to check that we have the factorization. That is equal to okay, and then let's just try to show that x1 is independent of x3 given x2. Okay, so we know that if we look at the joint distribution, x1, x3 given x2, that's equal to f1, 3, x1, x3 over f2 of x2. So that is equal to the integral of and then we want to integrate that over dx2, dx4, sorry, let me just write that out. And then we want to integrate that over x2 and x4. And then for f2 of x2, you can write this out as so this is going to be integrated over x1, x3, and x4, because you just integrate over the variable that you're not interested in finding the marginal for. Okay, and so this you can kind of show that sorry, so wait a second here. So we So I'm gonna this is something you can check yourself, but I'm going to just okay. So the denominator you can do by just integrating out the x1. And for the numerator, sorry, let me do this properly. So the integrals with respect to x4 are all going to cancel out. So so you can kind of just re-express this without all the x4s in there, and you're just going to get x2 and then dx2. Okay, and yeah, so with the cancellation of the x4s, this is what we're going to get. And similarly for the denominator, so we can take out the x1 on the numerator. And on the denominator, the x3 just gets integrated out as well, and we end up with because you're just integrating out the marginal, you're integrating out a conditional with respect to x3, so that just gets integrated out, and then you just end up with this quantity in terms of x1. And so this is exactly just f1 of x1 divided by f2 of x2 times the integral of dx2. Sorry. So this is and then this is going to be equal to f1 of x1 given x2 times f3 of x3 given x2, because the x3 given x2, like the f2, so dx2 just is equal to okay. All right. So yeah, sorry for that long-winded calculation, but the main point of that was just to show that so therefore we have that x1's independent of x3 given x2. And I guess you can sort of see why I'm not going to prove this result in general, because it's just a lot of messy integration. But that's just to give you an idea of like this relationship between conditional independences and the factorization. So just to summarize all that, so if we want to represent DAGs, there's obviously the there's two different relationships, two different, but I should say but equivalent relationships between the graph and the distribution. The distribution f of x1 through to xp. The first one is the factorization, which just asserts that and the second one is this conditional independence / dependence, which just asserts that xj's, or I should say, there's an edge between xj and xk if and only if xj is dependent on xk given the parents of xj and the parents of xk, but not the points xj, xk themselves. Okay, so sorry, it's a bit messy, but it was defined. It was defined earlier. Okay, so now let's take a concrete set of examples, and so these are referred to as linear structural equation models. And these are models that you can you can look up. They date back quite a while in sociology and psychology and various other fields. But the basic idea is that so we have our variables x1, x2 up to xp, and then we basically just say that xj is equal to sum the k in or it's like so So I mean, I'll describe it in words and then I'll give the equation. So it is it's the same as standard linear Gaussian model. But covariates are parents, and that's this connection to graph that we're going to parents of node according to a graph. So this is a nice model because it's going to be concrete and have parameters. So this is the structural equation model. I'm going to just refer to them as SEMs. And okay, so we have a different model for each j. J equals 1, 2 up to p. Xj is equal to, we're going to have some standard mean plus, we're going to look at the parents of xj, and I'm going to use this notation that k is just the parents of xj. And then we have these coefficients akj times xk plus epsilon j. So here we have that mu j is like a shift or mean parameter. It isn't exactly necessarily the mean of xj because the mean of the xk's are factored in. And then we assume that the epsilon j's are normal with mean 0 and variance sigma j squared. And then we also assume that epsilon 1, epsilon 2 up to epsilon p are independent. Okay, so we have this so we have that akj, this is the, so I guess we'll say that so the model parameters here is the mu, which is equal to mu1, mu2 up to mu p. Then we have the, I'm going to use this, let me just see. So going to use the notation, maybe sigma squared, which is sigma 1 squared, sigma 2 squared, sigma p squared. So this is these are both vectors now, so I'm just going to be clear, I'm just going to have that. And then we're going to have this matrix, I'm going to say A, which is in R to the P by P, okay? And we're going to say that AKJ is just equal to AKJ, okay? So we can kind of write this in matrix vector form like this. Okay, and note that A is related to graph G equals VE through parents, because note that we have that AKJ is not equal to 0 if and only if xk is parent of xj. Okay, so another way to interpret this is that, so I'm going to go again into matrix vector form, we have that if we let x equals x1, x2 up to xp, then we have x is equal to mu plus, and then we're going to have a times x. So it looks kind of like it's an equation, like x clearly depends on itself, and then we have plus epsilon, and then we have that epsilon is a multivariate normal with mean 0. So I didn't say this explicitly, but the mean 0, and the covariance is D, where D is a diagonal matrix with djj equals sigma j squared. Okay, so can we find the distribution of x in closed form? And it turns out that we can, because we have this we've got this scenario where we have a linear model, or you can think of it as p linear models that are all normal. And so when you have linearity and things are normal or Gaussian, you can usually do calculations quite nicely. So we have that okay, and then we know that we can rewrite this as I minus a times x. So this is the p by p minus a times x is equal to mu plus epsilon. And it turns out that if the matrix A corresponds to a DAG, then it's always invertible. This I minus a is always invertible. It's equal to this. And then we have that this is multivariate normal with mean 0 and covariance D. So mu plus epsilon is multivariate normal with mean mu and covariance D. X is going to be distributed as multivariate normal. And then we're going to have, this is the mu, and then inverse D times I minus a inverse transpose. Okay. So this is the mean of x, and this is the covariance. Okay, and note that if A is a DAG, or if let me just say G is a DAG, I minus A is guaranteed, or if G is a DAG, I minus A is guaranteed to be invertible. Okay, so so we can so the dependent structure of x is encoded through sigma, which equals to I minus A inverse D I minus A inverse transpose. And again, this is all like fairly abstract at this point. So the question is like, how can we relate this to conditional independence or factorization or what we've learned so far? And I guess the last comment I'll just leave you with before we kind of go into this in more detail in the in the next lecture. We have that xj is in so we have this equation plus the mu j, right? So therefore we can say that xj is independent of therefore if xl is not in the parents of xj, then xj is going to be independent of xl. So so therefore from a factorization perspective, we have that fj of xj given x parents of xj is going to be normal with mean of mu j plus summation k in akj xk, and then variance of sigma j squared, and therefore the f of x1 through to xp is okay. And so we will see what that looks like in next lecture. So we're gonna put all of those conditional distributions together, and then we'll derive the overall joint from that, and that'll give us a different perspective of these structural equation models. Okay, thanks. That's it for today.